Hello everyone, my name is Jose Fernando Muñoz Zapata, and today, with my love partner Salome Buritica Oquendo, we are going to talk about environmentally responsibly redox chemistry. This presentation it's about an article, and the article talks about an experiment or an example of combining oxidation methodology without chromium waste. The presentation are distributed in five important parts. First, we have the abstract and some keywords, then the introduction, the methodology of the experiment and the results, and finally some conclusions about the article and the experiment. The abstract have environmentally conscious redox sequences using MACTRIF, a recyclable oxidant. The product is identified and confirmed by melting point and IR spectroscopy. The highlight green chemistry use MACTRIF, that is recyclability, reduced by chromium 6, and the integrates redox chemistry, stereochemistry, and analytical techniques for sustainable lab practice. And the keywords are its redox reaction, MACTRIF, recyclable oxidant, benzoin oxidation, benzyl reduction, mesohydrobenzoin, green chemistry, melting point analysis, IR spectroscopy, stereochemistry, and analytical method validation.
Okay, I'm going to start with the introduction of the article. It talk about the redox reactions are fundamental in organic synthesis, and undergraduate chemistry labs often include examples that use chromium 6 as an oxidant. However, there is growing concern about the environmental impact of chromium waste generated by these reactions. In response to the need to incorporate green chemistry principles and demonstrate that chemistry can be beneficial rather than harmful to the environment, this experiment introduced a cleaner methodology. And the overall objective of this investigation is to present a simple and environmentally responsible reaction sequence that illustrates the reciprocity of oxidation and reduction process using MACTRIF, a recyclable oxidant.
Okay, guys, for the part of the methodology, the experiment is divided in two steps, in two important steps. First, the oxidation of benzoin to benzyl and the reduction of benzyl to mesohydrobenzoin. For the part of oxidation of benzoin to benzyl, first we need to add to a solution of benzoin in toluene, then the mixture is heated to reflux, and the reaction is monitored by TLC, that is thin layer chromatography, to track its progress. And it's check if the reaction is complete. If the reaction is complete, the MACTRIF solution is cold and decanted. Then the residue is washed with toluene. The combined solution is filtered through sealed, and the solvent is removed with a rotatory evaporator. The obtained residue is recrystallized, and finally, we have the benzyl. And the benzyl is characterized by melting point and IR spectroscopy. Then we have the second part, that is reduction of benzoyl to mesohydrobenzoin. And first, the benzyl is dissolved in ethanol. Then the sodium borohydride is added to the solution, and it's observed if the color disappears. If the color disappears, it's diluted with water and heat. The solution is cooled slowly to precipitate the product, and the product is collected by vacuum filtration. Lastly, the mesohydrobenzoin is characterized by melting point and IR spectroscopy.
Now, talking about of the expected results, we have that according to the article, typical or expected yields from the oxidation step from benzoin to benzyl are around 80%. Low recovery are usually due to insufficient or improper washing of the matrix, or in some cases excessively long reflux times. For the reduction step from benzyl to mesohydrobenzoin, typical yields range between 30 and 35%. Under the described experimental conditions, the mesoisomer is expected to precipitate predominantly. This outcome opens the door to discussions on stereochemistry, including the theoretical number of possible isomers, their formation, and the reasons why only one is isolated. The products from both steps, benzyl and mesohydrobenzoin, are characterized using melting point determination and air spectroscopy.
And finally, for the part of conclusion and relevance, this laboratory exercise allows students to explore the reciprocal nature of oxidation and reduction reactions in an environmentally conscious manner. The use of MACTRIF as an oxidant eliminates potential health and environmental risks associated with traditional chromium-based oxidants. Although MACTRIF may initially appear expensive, its ability to be fully recycled at a low operational cost makes it a cost-effective long-term option. In addition to reinforcing redox chemistry concepts, the experiment emphasizes essential laboratory techniques and places them within the context of green chemistry principles, preparing students for more sustainable chemical practice, and this experiment serves as a valuable example of organic chemistry education as sustainability principles can be integrated into the university curriculum. Okay, guys, this is all for us. Thank you for supporting. Thank you for your attention, and goodbye.